Okay, so today we are talking about the normal form games. We already, in the last lecture, two lectures, we talk about probability theory and we discuss, important things. We still have one more session about linear programming that we will talk, but I think for now we can talk a little bit about the games and then we have another session on linear programming, which is another necessary thing for this class. Good. Now, let's talk about the normal form game that we have started previous time. So this is the game that we played previous time. This was the chocolate, but we changed it to carrot game. And let me go to this one. And as you see here, okay. So this was the case that we have two people and they could come and we had two actions that these people could take. Take one piece of chocolate and you may keep it, or take 3 pieces of chocolate and then they'll go to the other place. And we had some different assumptions that we played based on that. And by the way, this is a website that you can go and you will see more about this chocolate dilemma. But so we had some assumption and some discussion about it that we have done it in the previous session, that here when we have two players, the other player is a stranger whom you'll never meet again. The player is an enemy, the player is a friend, is a computer program. And take one means you take two chocolates instead of just one. We had also this thing that the two players could actually discuss about that and about the options that they have it, and then they will come and do the actions simultaneously. So there is one more case that I want, like actually two more cases. So here there are, you can have like thousands of people that they are taking essentially the game. That we cannot do it here. But I wanted to do two more example of this one. One is the case that you are playing the game repeatedly with the same person. This is called repeated games. There are lots of analysis of them. Generally, there are this concept of, we have actually introduced this price of total anarchy, and there's this concept of regret minimizations that these people are regret minimizer players. We will talk a bit about them very late in this course. But there is also this option that instead of like chocolate, what about if there is money? And then what are how much money is important? So I want to do these two experiments as well, because I think these are like somehow, you will see that these are some initial introduction to this class and the games and the actions that we are considering in this class. So let's play, these two, and then we will continue, and then we talk about the lesson learned, and then we will continue with the rest of the class. So let me just... great. So we played this game, essentially, that two people are just playing repeatedly. And first we have done it with take one, take three things. And you see, this was an interesting case that the people started, the person A and B, and then first they were some kind of essentially, I will say, this coordination in some sense among them, that there was 1-3 versus 3-1. But then they later, they agreed that, okay, let's have it 3-3. and maximize ourselves. This is actually a good. This is like it is. These things, if you just think about it, these are just the real world or real life problems. And a good example of this is like that you have a roommate. He or she maybe had some music loud. Then you will go and complain to him or her. She said that, okay, you are also not washing the dishes. So that's one tree essentially. And then, then you will repeat. If it is the next time that you will go there and then again the music is loud, you will go there, but again, you have not done the dishes. After some time, she or he decide that, okay, I should maybe have a music a bit not that loud, and you also start doing the dishes. And you will continue that. Good? So that's essentially the game of life. So this is not just, you see that. So this was the second one that we have done it with money, 2,500 versus 3,000. And you see that, and we will talk about it, the money is something, is more catchy in a sense. And also here, the ratio is important. 2,500 versus 3,000, and you can think about it. The people generally are risk averse. So, okay, why should I do any risk essentially? Even in the repeated case, they still took that 2,500 because that is something that is guaranteed. Yes, you may get $500 more, but who knows? You may lose all of it. And again, this is something that is a real life thing, that the people about the money, what's the meaning of that? It means that you generally can offer the people some, if you want to settle with the people, like for example, in a court or anywhere, that is, if you can offer some cash, they may just take it because they never know what will happen in the court or other things. Of course, it depends on the amount, as I mentioned. The ratio here is great. So let's go to the next page. Need to just clear all. Okay. So these are, as we discussed, so these are, there are different assumptions. So it can be, the game can be complicated. The objective that the people are considering in these games can be different, essentially. Like essentially, they may try to make friends. They may, this might be an opportunity that two people become friends, essentially. Or, they want to look good in the class. That's another motivation. These are, or they want to maximize their money or chocolate or something. So these are different things. And the issue is that, how do we handle all of this in games? This is the concept of utility function that we will discuss. And then in some sense, we turn everything in terms of money. It may be not known even what are the exact numbers, but that's the simplest way that we can analyze this. So this is the case. So, for example, there are some studying about this that we can say that if each player just want to maximize how many chocolate he or she gets it, and no player cares about anything else, that is also important. Just the objective is to maximize the number of this. Both players understand all of the possible outcome, and this is common knowledge to both players. The concept of common knowledge is also a bit tricky that we will talk about it. But for now, just take it as a common knowledge. But even that is not that simple. Then in this case, this is the case that we know that then each player will take one piece of chocolate. So this is, in some sense, we will talk about it. This is a Nash equilibrium. What's the meaning of that? It means that if the other player does not want to change his or her strategy, you will not change it. This is some kind of equilibrium, the 1-1, actually, not 3-3. Because the issue is that if you know that the other person is doing 3, if you want to maximize your things, then you may essentially decide to go with 1, because then you will take 4 instead of 3. So this you can also prove that if they can talk to each other beforehand, it won't change the outcome. Still 1-1 is the thing that they should get it. If you repeat any fixed number of times, it's still the same outcome. But if you do repeat an unbounded number of times, they may take 3 instead. But for a bounded number of times, still 1-1, take 1 is the one. And the question that whether these are realistic or not. I mean, this is a game. Again, the game theory probably is the most complicated things, especially if you see the world. And everything is a game. So if you see the world like that, then the solutions, of course, would be not easy to answer about different things. So games are not just computer games, are not just football games or basketball games or something. The whole life is a game. At least you can consider it. I mean, at some point you may stop seeing that, maybe see a better, more or less, favorable things about the world. But I mean, the realistic thing is that it is a game. What was that? Always game of life. Yeah. So that is the things that we are talking about. And good. Even that actually it is interesting, given there are some studies that shows that, for example, the people who think that, for example, they like helping the people, maybe say this is of course, this is then you can consider the utility for those people. And it has been turned out those people that they are like, I mean, at least some studies that if they are helping the people, the main reason is that they will be more satisfied, they will be more happy. So in some sense, they are also increasing their happiness. And this is maybe mental happiness. Maybe it's not in terms of money, but sometimes mental happiness can be. When I solve a problem which was open for a long time, I will be, super happy. Not money cannot describe it. At least some limited amount of money cannot describe it. Good. So here are the games that we are considering. They will be in the normal form games. This is important. Or let me just annotate it. Okay. Here in the normal form game, we are generally consider n-person game, n-person normal form game, which includes the following. An order set n equal to 1, 2, 3 to n of agents or players. Please unmute if you don't want to talk. Good. So we have n players. Each agent I has a finite set AI of possible actions that he or she can take. Let me actually give me 1 second. Good. So yes. So we have an ordered set n equal to 1, 2, 3 to n of agents or players. And then this is each of these guys or girls has a finite set A of possible actions that they can make. So we can consider the whole thing as an action profile, which is an n tuple A1, A2 to AN, where A1 belongs to the set A1 of all actions of the first player, A2 belongs to the actions of the second player, and AN belongs to the actions of the nth player. The set of all possible action profiles would be this. The cross product, because essentially, yeah.
The action profile meant to be the actions that the agent has taken.
Yeah, the action okay. So action, you have AI. The set AI is means that all the actions that a player can take, the player I can, and we know say before. Action profile, you can consider some future things or the past things, but essentially it's the action profile. When we talk about profile, generally means essentially a vector of actions. That the first one is the action of the first player, the second is the action of the second player, and the nth is the action of the nth.
Okay, so the action profile is for each round. What each player?
Yes, for each round. If you consider some kind of simultaneous game, each round that we consider here the simultaneous case, that all of them at one point they decide, to take the actions. And this might be not even simultaneous, but it might be the case that the people don't know. It's like, okay, you are starting the game, choose your actions, now bring your final actions. Like the way that we have done it in the class. The people they're writing the actions. One person may finish it before that, but we will collect all the answers and then we form the action profile. So that's the definition of an action profile. And it is important. We are talking a lot about this. So also for each like agent I has a real valued utility or payoff function. So what is that? This is the UI of an action profile. It means that if all the people are taking these actions, what is the payoff that agent I is getting? So it is UI, utility for player I. So it is I's payoff if the action profiles is A1 to AN. So this is called a normal form games, and generally we can represent it as a matrix here as we have done it here. So these are like for the player, say this is the player one, generally this is the player two, and or it can be vice reverse. Then you will do the actions that each of them can take. So here it was symmetric because they can take the same actions, but it might be not symmetric. And then here, what do we write? So here it means that in the action profile, take three. So this action profile that both of them are doing the take three, how much is the utility of the first player, which is three, and how much is the utility of the second player? So if both of them take three, then it goes to the other person would be 3, 3. That's a utility function in the chocolate or / carrot game. But if like player one takes three, the player two takes one, then in this case, generally when we are doing that, this is for the row player and this is for column player. So this goes to this guy, girl, this one goes to this. So here, if this is take one versus take three, so then 4 goes to the player two in some sense. Maybe actually it's better to change it. This is player one and this is player two. So in that case, then 4 goes to player one, which is the raw player, and 0 goes to player two, which is a column. This is symmetric if we are doing the other one. This is called symmetric game. And finally, last but not least, if both of player one and player two, they take one, then it would be 1, 1 and goes to each of them. So this is essentially called payoff matrix or utility matrix. And each cell of, so like you may have actually more than, if you have more than 2 players, say if you have 3 players, instead of this kind of things, you may consider as a matrix essentially. But not the game, the actual one, but not the movie I meant. I don't know whether there is a game also maybe matrix or not. So here, each cell of this cube, if there are 3 players, 1, say 2, and 3, then each cell of this cube it says what is the utility of each of these guys. And this is important. That's the way that we can represent these games in computers, as like for computer programs as well. Yeah.
I have a question about the set of all possible action profiles.
Yeah.
So each of the elements, like A1 through AN, is a vector. Is that right?
A1, A2, these are sets. A1 to AN, these are the sets. The set of actions that the player, like A1 is a set of actions that player one can take. A2 is a set of actions that
capital A1.
Capital A. Capital A. Yes.
So instead of multiplying, wouldn't it be the union?
Yeah, that would be union of all possible actions that all players can take it.
Yeah. So then, why does it mean X? What does the X mean?
X means essentially like product of these things essentially. Is it the product of the vectors? The Cartesian product. Yeah, I think this class is, I mean, we are talking a lot of math, and that's the thing that we have done it with probability. You need to actually know algebra as well, because that also plays an important role. Yeah.
So like, is player one going to usually be the y-axis, player two usually be the x-axis, or is that?
Yeah, I mean, generally we are saying that player one is the row player in this matrix. This is this row essentially, you see, the row player, and the player two would be the column player. That's a typical. I mean, this is essentially, you can say, I mean, I don't know, X and Y, you can have it X and Y either way. But here, row and essentially column is clear for this matrix. And this is important because, why is it important? Because this is the way that we can represent these games, the input of this game in a computer, for a computer program. So what would be, so if you have, say there are two players and each of them have, say, n actions. So two players, n actions. What would be the size, the input size, or how much is the space we need to represent essentially the utilities of these people? Yeah?
2 to the n, or n squared.
What about you? 2 to the n or n squared? N squared. Yeah. So in this case would be n squared, because I mean you can consider this one. You see, this was the thing. So there are. This is the first player, n actions. He has it. He or she has n actions. So in each of these, you can represent this one as essentially an array. And then each cell of the array say that what is the utility of the first guy and what is the utility of the second. So essentially would be n squared. If you have two players, n actions, the space that you need it would be n squared. Now let me change this one. What about if we have n players, each of them have two actions? How much space do I need to represent this case? Yeah. So there is one who answers 2 to the n. Any other solution? I mean, the people at Zoom actually, please unmute and answer if you want. So it's say 2 to the n. Any other answer? So we have n players, each of them have two actions. How much would be the space that we need to represent this?
Maybe n squared.
Okay, so this is another thing that you need to work actually. This is the basic of combinatorics. So here, if we have n, so this, in that case, you can actually write it down. You see, how many action profiles do we have? That will be the size that we need. So for the first player, we have two actions here. And then for the other guy has two actions, and the other one has two actions, and so on and so forth. So it means that the total number of actions are 2 to the n. Correct? So if you want to represent it, you can represent it as a matrix. But are we done is 2 to the n is enough? I say, what is the order of the space? Again, this is like the one that we know, for example, for introduction to algorithms or other classes. We are not done. I have n times 2 to the n. Why? Because in each cell of this, high dimensional matrix, I need to also have n numbers for the utilities of each guys or girls. You see here, when we have 2 players, then we have 2 numbers here. But if you have n players, then you have n numbers. So the actual space in this case, if we have n players, 2 actions, it would be n times 2 to that. Yeah.
Wait, so for 2 players with 10 actions, would that be 2 n squared?
Yes, but in terms of, yes, the correct one is 2 times n squared, essentially. But, in terms of order, it would be n squared. But here, it is n times 2 to the n, which is a bit larger than 2 to the n.
Right, that makes sense.
In terms of order. So this is the part that we talk about computational game theory. So it is not just the game theory, but you need to say that this is the game that you will get it. So what is the general idea? The general idea of this class, you can think about it. You can consider anything as a game as we talk about it. Try to formulate it. We will talk. So in some sense, we say that, okay, this is a game. We give the examples. We say that, okay, you can formulate it as essentially as a formal game or normal form game. We will do that. Then we will represent it. How can we represent it in a computer program? Because that's a computational game theory, not just game theory. So then you do that. And then you will write programs then, based on the assumption, maybe find an equilibrium, for example, different concept of equilibrium. And again, equilibrium in some sense are settlements, that these players, I don't know, 2 to n players, they settle on some cases. There are different definitions and they're doing that. That's the whole class that we are talking about. And of course, each of them needs both programming, essentially math, as well as, some kinds of social sciences that, how do we want to model this whole thing as a game? That you may need to understand better, essentially, the game and also the utilities of the function. To make this, we are talking about utilities, but these utilities are not given to us that easily because, as I mentioned, the people may try to help others and at the same time they enjoy it. And this enjoyment should come in terms of utility function. Otherwise, we cannot analyze it. This, to understand it, what is the factor enjoyment you want to do it, you need to do social sciences or some essentially study. So that's the thing, that lots of essentially sciences are really interacting with each other, like math, computer science, social sciences, and others essentially, that they are coming and all intersecting in game theory. And again, it is important because you can see the whole world, each set of events of the game, or each events or each a sequence of events in a real world of the game. And that's the thing that game theory is important. So that's the whole thing that we are doing. And this is, as I mentioned, this normal form game is a very popular game that, we can, because especially we can represent it in terms of, we can do it also in computers, etc. It's a very nice and concise way of representing these games or somehow formulating the games. So that's a good thing. Now let's clear everything. Good. So that's the thing that we talk about it. The one that we talked so far was about the prisoner's dilemma. So this game that we played in some sense is this game, Prisoner's Dilemma, is very similar to Chocolate Game. But it is a very famous one. This is one of probably the basic example of a game theory would be Prisoner's Dilemma. That, this is the scenario that the police are holding 2 prisoners of suspect of committing a crime. For each prisoner, the police have enough evidence for 1 year in prison, but they want to get enough evidence for 4 years in prison. Then, this is the way that they are doing that, the police, they tell each prisoner, if you testify against the other prisoner, we'll reduce your prison sentence by 1 year. Again, these are everything is like some kind of settlement that they are doing that. So in some sense, here, in the simplistic way, these are two essentially prisoners that they are playing game with each other. But in reality, actually, police is also a player. They have maximized their things as well. I don't know what is the maximizing here. They want to pay maybe free food to these people for more years, but they may do that. But again, this is important. When you see the game, try to see a bit beyond the box, essentially, above or beyond the box. So we are considering two actions cooperate with the other prisoner. So here it means that cooperate means refuse to testify against him or her. And then defect. Defect means testify against that. So the idea is that if both prisoners cooperate, then they will go essentially only 1 year in prison, each of them. However, if both prisoners defect, they will go to prison essentially 3 years, because 4 years they have that, and because they have cooperate 1 year extra, so they get it 3 years. And if one defect, the other one cooperates, then the one that cooperates goes for 4 years in prison, and the defector goes essentially for free. So this is the normal form matrix that we can represent it. So this is like example of the one that I have mentioned. So we have a game, and we try to essentially represent it with the matrix such that we can do some operations on it. And again, you may at any time, if there's a game, it might be too complicated. You may break it down. Some players you may want to take them out of the game and just write the game for the subset of them. That is totally fine. You may do that. It might be not as general as possible, but sometimes you have so you may think about, say, okay, for example, here, you don't want to consider the utility of the police. So you will just take the police out of the game, and then you consider these two prisoners. So in this case, I mean, this is now we are representing that if they're cooperate -1. If this is essentially defect cooperate would be 0 for the first guy, and then -4 for the second guy. These are the number of years in jail, because the one that essentially, here, if one defects and the other one essentially cooperates, then as I mentioned, so that would be essentially for the person who defects. The person who cooperates essentially goes 4 years here, and the person who is sorry, vice versa. So the person who defects essentially goes 4 years to prison, and then the person who cooperates goes 0. And if both of them are defecting, then both of them get -3. Good. So this is for this game, but I mean, you can so you can represent this one in a different form. So we use this form. This is the form that we have. But there are other ways that you may consider this. So it is equivalent to just add two things. So take 3 would be 3. Is like this take 1 essentially would be 4. And so this is essentially the game that we have done it, the chocolate game. You see, this is the same thing. And how did we get from here to here? Essentially, if you see that we are adding 4 to each entry. From -1, it goes to 3, -1 goes to, and then 0 goes to 4, and so on and so forth. The game theorists may consider something a bit different. They say, I mean, instead of this, they say 3, and then 5-0. So this is like when they represent the prisoner dilemma, they may have this 5 essentially instead of 4, because I mean the amount of defect and the years that you go prison might be different. But anyhow, so in the prisoner's dilemma, in general form would be something like this. we have this CD, and it is a symmetric game. Both of them, they will get A and A if they both cooperate. If one defects, the other one cooperates, they get C and B. Vice versa would be B and C, and then D and D. And in the general form, we have this issue that C should be greater than A, should be greater than D, should be greater than B. So what is C essentially? C here, for example, is this one, that like if one cooperates and the other one essentially defects, the number of years in prison, that should be greater than if both of them defect, essentially. So these are just some assumptions. You can think why this assumption makes sense. It is a good exercise to think about it, why for prisoners lemma is there. I mean, you can also search on the web if needed. But it is interesting. It's some kind of good exercise to think about it. Yes. So this concept of utility function. As I mentioned, so utility function is a tricky thing that may actually need some social science or other things. Because how do you want to put, by utility, we put everything in terms of essentially just some numbers. That's the whole idea. That anything in the world, you can, at the end of the day, you can represent it with some numbers. So is it as general as possible? There are some studies of that. So the idea, I said, that if you don't want to take the utility function necessarily, the preferences of a rational agent must obey some constraints. Again, so I said I have some preferences. Maybe I don't know what is my utility number. I have just some preferences. These preferences, generally, they should have some constraints. Of course, there might be, we will call, there was actually some games, it is called I mean, the player might be unreasonable or irrational, essentially. They may not have these, I mean, conditions, but at the same time, you say that any person, even irrational, has some constraints. So those that are more rational, we can actually model them with their utility functions. So the general constraint is the orderability. What's the meaning of that? If this is so this is my preference. If if outcome of the game, either this outcome is better than the other outcome, or this other outcome are the same as this outcome, or these two are equivalent. These are my essentially note that what is the outcome of the game? When these people are playing, they are taking some actions. Then these actions, based on these actions, they may get some utilities, correct? But whenever these guys, they are taking actions, it means that at this point, there is some outcome for the game. And then we are talking about that outcome. What are the utilities for these people at that with those outcomes? And again, so here, essentially, we are talking about A and B. So there is some outcome of the game. And this outcome should be either one is preferable than the others, or the other one should be more preferable, or they are equivalent. So somehow orderability or completeness, we can compare them. And the transitivity. If this outcome is better than this outcome, and if A is greater than B, or more preferable than B, and B is more preferable than C, then A is more preferable than C as. So this is the transitivity. So here, that's the thing, that the idea that I have mentioned. If agent choice are based on this kind of rational preferences, then the behavior of these people can be described as a maximizing of some expected utility. And here we talk about expected utility because some randomness might be in the game as well. That, I mean, you can, almost all games that the people are doing, or lots of them essentially, they have some randomness there. So this is a theorem due to Ramsey 1931, or Von Neumann and Morgenstern 1944, that given preferences satisfying the conditions above, there exists a real valued function u such that u of A is greater than u of B, if and only if A is more preferable than B. And U is called the utility function. Good. So as I mentioned, so this kind of utility function is not a trivial thing. If there are some rational things, and for example, these are some of these conditions, this is a theorem by Ramsey or von Neumann that says that under these conditions, there exists a utility function. What is the property of utility function? Is that if the utility for A, outcome A is greater than the utility for outcome B, then A is more preferable than B and vice versa. And here U is called a utility function. So that's the reason that we consider in this game, because it's more computational game theory, we try to more simplify and get a utility function, but it is not always easy, essentially, to do that. Some cases it might be more complicated. Good. So utility scales, that is important. As we discussed for this prisoner's dilemma, you can have some equivalent game. So you can say rational preferences are invariant with respect to some kind of positive affine or positive linear transformations. So what is a positive affine or positive linear? It is essentially this function. That u prime of x so is equal to c times u of x plus d. And c and d are both constant, and c should be greater than 0. That is important because if c is less than 0, it may change the order. So you can essentially multiply the utility of a person by some number, which is greater than or equal to. I will say greater than 0 because 0 makes it essentially 0 and makes nonsense. So it should be greater than 0. Or you may add anything. Additive, you can add positive or negative. That's fine. But when you multiply, it should be some c greater than 0. And in that case, given that preference thing that I have mentioned, then U prime models the same set of preferences that U does. So in some sense, if you do this operation, you don't change the preferences. You may consider the normalized utilities. In this case, you define essentially the U of max for a person is 1 and U of min is equal to 0. So you can always assume that the maximum utility and minimum is 0. Because for each person, you can change it, this one with appropriate C and D, such that you will make everything is between 0 and 1. That is called normalized. That is also, again, good exercise to see how come if somebody gives some things you can, and this you can do it for different players separately, essentially, or independently, by the utility function. Utility of each of these people, you can just make it between 0 and 1. So let's see some examples here. So assume that, so this is the utility scale for the game. That suppose that all agents have a rational preferences. And this is a common knowledge to all of them, that everyone knows that it is a rational. We are talking about common knowledge, but we define it more formally later. So let's C and D be some constant C greater than 0. For one or more agents, we can replace the pay of xij of this agent with C times xij plus D. That's the definition that we have mentioned. So this game still has the same, models the same game with the previous preferences. So let's see an example. For example, we have these games, these are the actions of these guys. And then you may multiply, for this player 1, you may just multiply all the payoffs by C plus D. You will do that. And then you can do independently for the second player as well. Let's see, a concrete example here. So here, for example, in the prisoner's dilemma, you had these actions, essentially CD and CD. And then what will happen here? So here, you will consider for the second player you can get an affine transformation. How? I mean, here we are just decreasing everything. So here, essentially, in this case, C is equal to 1. See the multiplier is equal to 1, and D is equal to -4. So if you do that, so for the first player, we don't do anything. For the second player, we are just essentially C is 1. We don't change it. We just do it -4. So -4 here, -4 here, -4 here, and -4. And now from here, we don't change this, guys. Now here, you are doing another affine things. Again, here, C is equal to 1, and D is equal to -4. And now you are doing for the, essentially, first player. So it is, now you make it -1, because you just do it -4. So from 3, it goes -1, from 4 goes 0, and so on. But what about these guys? Can we have such a things? So, by the way, to see whether 1 is there, essentially you need to do equations, write some equations, see whether you can find this C and D. If you can find this C and D and C greater than 0, it means that 1 is the positive affine transformation of the other. But what about this? So in this case, note that all of these guys, so these people, we are keeping all of them the same. Only this guy, we are changing it to 5. So if you write some equations for C and D, you see that, I mean, for the first guy, we don't do anything. For the second guy, we are changing it. And if you write it, you see that there is no C and D that you can do this transformation that goes from one to other. And then only one entry changes, goes 4 to 5. The same thing here also. Here, we are also from here to here. Everything is the same except this 4 and 5, essentially. Again, you can see that there is no C and D that you can do it and you get this result. So that is a good exercise again. Please do it. And I mean, see this affine transformation. You should see how you can go from one to other. Because in some sense, what is the idea of this affine transformation is that, I mean, yes, these games might be complicated. We cannot consider all utility function, but let's keep understand the simplest case. And generally, the simplest case that we are considering is this one. The one that I mentioned, these are like when the case that the utilities are all between 1 and that the utility. Yes, so this is the one that we care the most, is that the utilities are between 0. Good. So let me just think. So this is the one that actually we discussed. Let me just make this one is clear. So this is the one. Which of the following lotteries you will choose? We actually discussed somehow this one when we played this game with 2,500, 3,000. 100 chance of receiving 3,000, 80% chance of receiving 4,000, but 20% chance of receiving nothing. So how many people are choosing A? How many people are choosing B? Okay, so the number is like interesting. Let's see now another example, which is interesting. So here it is. So here you will gain. So here it says that which of the following lottery you will choose? 100% chance of losing 3,000, and then 80% chance of losing 4,000. How many people are choosing C? How many people are choosing D? Okay, so let's do the numbers essentially. So actually, this is something from Kahneman and Tversky, 1979. So in both of these games, we can compute the expected value. So what is the expected value in this case? So for example, here you can compute in the first case. So you get in the first case is the 100%. So this is 3,000. What about this is the expected value? Here we need to use probability. 80% of receiving 4,000. So it would be 0.8 times 4,000. plus 0.2 times 0. If you compute this one, would be 3,200. Good. So you see that action B, you will get more money, 3,200. However, most people would choose action A because this is a guarantee. This is called, generally, when, this is again, these are some of the things that your social sciences are coming. In terms of numbers, this better, B is better. But lots of people still, they don't want, when they comes, they gain, they try to be risk averse. They don't want to risk. Let me get the 3,000. The same thing that we discussed, like 2,500 versus 3,000 in chocolate game, essentially. That the people wanted to do. Now the same thing, now that you're losing. So the losing is that if you compute again, so here you are losing essentially 3,000 minus 3,000. Here you are losing essentially the same thing you can compute as above. We are losing 3,200. But the people, when they are losing the game, the people are more risk prone. What's the meaning of that? I say, okay, who knows that? If I lose 3,000, somebody said you should get 3,000 now, and the case is settled before the court, or you can go to the court, but the chance it might be, I mean, you are losing 3,200. They say, okay, who knows? Still, there is some probability involved. Maybe I will go and don't do these things. So in that case, actually, the people are risk prone. I said, okay, let's take the risk because this is something that are doing that. This is again some, you can look at this link and find about it. And of course, see there's this reference. But these are the things again that the social sciences are coming with the concept of numbers. And this is, in terms of expectation, is not a beneficial thing, but the people are doing that. So you may think about, okay, maybe in that case, if it is the case, there are some other factors that are important. For example, you can consider not only if we talk about expectation, but also variance or a standard deviation is important. What is the, I mean, with which chance essentially I am, if I go to the court, I will lose 3,200. If it is almost certain, still they may get 3,000 versus 3,200. So these are the things that this is somehow the play between like math and social sciences. So, okay, yeah, this is not exactly like that. The people are choosing differently. Then math comes to the help. Maybe there are some other factors that we need to consider. They will consider that one, then they become closer and closer. And that's essentially the whole thing that we are doing in this game. Yeah, so that's essentially for now.